Now we turn to deletion. We already have a pointer to the node we want to remove, so let's see how few steps it really takes. Let's delete a node when we already hold a pointer to it. This makes the job local. We just point its two neighbors past it, then free it. There is no search here, so we do not pay the big O of n that chapter 4 paid to find the node before it. This is the list before. We want to delete x, which sits at 1000 and holds the value 20. It is in the middle of the list 10, 20, 30. Node 10's next field points at x, and node 30's prev field points back at x. This is the list after. 1000 is freed, shown in red. Node 10's next field now points straight at node 30, and node 30's prev field points back at node 10. The list is now 10, double arrow 30. The key idea is 2 writes, not 1. First we set x arrow prev arrow next becomes x arrow next. That fixes the forward chain. Then we set x arrow next arrow prev becomes x arrow prev. That fixes the backward chain. And only after both writes are done do we call free of x. We never free before relinking, or a neighbor would still point into freed memory. Watch out for one trap. You may fix only the forward side and think the node is gone, but if you skip one write, one direction still points at the freed node. The forward walk looks fine, yet the backward walk steps into freed memory. Always write both sides. Now let's do the delete one step at a time. The red node is the victim. We always relink before we free, so we never read a freed node. We advance with the arrow key. This is the list before. X sits at 1000 and holds the value 20. It is in the middle of the list 10, 20, 30. Step 1. We run X arrow prev arrow next becomes X arrow next. So node 10's next field jumps from 1000 to 2000. The old link to 1000 is gone. The dashed red arrow is the victim's own next link. Nothing points into the victim now. Step 2. We run X arrow next arrow prev becomes X arrow prev. So node 30's prev field jumps from 1000 to 3000. Now both neighbors skip the victim, but the victim is still in memory. We have not freed it yet. Step 3. Now we call free of X 1000 goes back to the heap. I ghosted in red instead of erasing it. The list is now 10, double arrow 30, and the delete is big O of 1. Now a learning check about a boundary case. We call delete node on X, and this time X is the current head. Which of the two relink writes is skipped, and what takes its place? Now the answer. When X is the head, X arrow prev is null, so there is no predecessors next to fix. Instead we set head becomes X arrow next, which moves the head forward. The second write still runs as normal, unless X is also the tail. This is the delete written in C. Even delete is only pointer work here. We start with a guard. If X is null, there is nothing to remove, so we return. Then we look at the node before X. If X arrow prev is not null, there is a predecessor, so we set X arrow prev arrow next becomes X arrow next. The predecessor now skips over X. Otherwise, X was the head, and then there is no predecessor to fix, so we move the head forward instead to X arrow next. Here is the second half, and it is the mirror of the first. If X arrow next is not null, there is a node after X, so we set X arrow next arrow prev becomes X arrow prev. The successor now skips over X. Otherwise, X was the tail, so we move the tail backward instead to X arrow prev. Both neighbors now skip X, and only then do we call free of X relink first, free last. Let's look at the cost. This is big O of 1. It is just 2 pointer writes and a free with no search. Compare Chapter 4's delete value, which paid big O of n to find the node before it first. Here we already hold the node, so that cost is gone. These are the two walks written in C. The forward walk starts a cursor at head. It keeps going while the cursor is not null, and after each node it follows next. The backward walk is the mirror. It starts a cursor at tail, keeps going while the cursor is not null, and after each node it follows prev. The two functions are symmetric. We only swap mex for prev, and we start from tail instead of head. Let's look at the cost. Both directions are big O of n time because we touch each node once. Both are big O of one space because we keep a single cursor either way. The only new cost over Chapter 4 is the second pointer's storage. We pay it once per node, not once per traversal.